Neural networks are certainly not new, but back in 2012, with the convergence of data, availability of data, the compute performance, and of course, better algorithms that triggered the new era of AI. If we fast forward to 2018, that's the era of large language models and generative AI. Model sizes are growing and growing at a much, much faster pace than Moore's law. For example, the transformer sizes are growing at 750x per 2 years compared to Moore's law, which is about 2x per 2 years. That has led to applications which, for me, I've read in science fiction. I actually saw a couple of articles in BBC, and one of the articles was on how long until a robot is going to do your chores. Today, it's certainly possible. Now, a couple of years earlier, there was an article in CNN which actually showed that AI won an art contest, and the human artists are furious about it. And the prediction of AI going forward is that the models are going to get larger and larger, and with that, the power consumption is actually going to go through the roofs. AI has certainly started, as we can see, has started pushing the limits of energy, chip production capacity, and data. We did an analysis of the operational energy use of AI chatbots. Assuming that we have 2 billion users and each user uses 5 queries per day, and there are 365 days a year. If each query consumes takes about 0.001 to 0.01 kilowatt hours, then the total watt hours turns out to be 3.65 to 36.5 terawatt hours. That's equivalent to 5 Hoover dams. That's a huge amount of consumption. A fruit fly has about 100,000 neurons. It does amazing stuff, right? Dodge dynamic obstacles. And they do that with about microwatts of compute power. The two-pen flying monkey that we developed as a part of this project, the power consumption for the compute was about 1 to 2 watts. So if I go further and go higher up the chain, go from fruit fly to, let's say, dogs and humans, the humans, it turns out, does amazing stuff that we do with about 20 to 30 watts of power consumption. Whereas if I were to use these data centers to play, for example, the game of Go, that required about 10 to the 6 watts or so. So when we try to compare, for example, AI versus natural intelligence, there exists a huge efficiency gap. There's been an evolution of the AI models. It started with multi-level perceptrons to convolutional neural networks. Depending on the applications that we look at, spiking neural networks, RNNs, transformers, which are the backbone of today's large language models, into Neurosymbolic AI. And most of the computations being in this particular case for all these application domains of the workloads, for speech, language, vision, it's basically the matrix multiplication. In order to handle some of these large-scale matrix multiplications, there's been an evolution in the AI, in the hardware. In particular, actually, the evolution from CPUs to GPUs to tensor processing units and NPUs. Point is that there's a need for really thinking about new architectures, new hardware, and what should those hardware try to do? Really take care of some of the inefficiencies that exist today. Most of the applications would require, for example, heterogeneous processing. They might have to deal with sparse and irregular access patterns, high memory intensity, or in other words, talking about the memory wall, can we alleviate this memory wall? And then finally, I mentioned some of these things on softmax, stand hyperbolic and all. And so those have to also do transcendental functions in an efficient way so that I can reduce that efficiency gap that exists today. I take a large scale, large language model, and if I have to implement it, the mapping is going to be very important. So one quick way of doing that would be to look at, for example, what's called the pre-fill phase, where in an LLM, it turns out 50% of the execution time is dominated by GEM operations, which is matrix multiplication operations. But in the decode phase, it turns out that one has about 90% of the execution time dominated by accesses to the DRAMs. So with that in mind, one can actually do proper phase-aware mapping, and that potentially gives you a good amount of improvement.
So, if you look at neural network accelerators today, and if you look at one of the large bottlenecks is the ability to store a lot of data. So there has been this push for higher density and higher capacity memory, particularly if the memory is on die, that you can integrate along with your logic. No matter what you have, you will see that more than 50%, 60% of the die today is just memory. The workhorse of the semiconductor industry is, of course, the SRAM, which is a six transistor cell. It's a very mature product. We scale it down all the way up to 3 nanometer and 2 nanometer today. The advantage of using RAM or any kind of resistive memory in a neural network or an AI accelerator is the higher capacity of memory that you're going to get, and the in-memory computing, particularly the analogish, mixed signalish in-memory computing. You can actually implement that pretty efficiently using an RAM kind of a technology. There are also other technologies on the horizon, particularly for memory. MRAM or magnetic RAM. This is again one of those technologies which has shown a lot of promise. PCM or phase change memory has been around for a while, which again poses some challenges in terms of endurance and write energy. Ferrofets is a new genre of energy which has been investigated, in academia and industry quite actively. It has a lot of the good properties of SRAM along with the scalability of some of these resistive memories. This is a full neural network processor with embedded memory and computer in a computing memory, and with all of these compensation techniques and calibration techniques, you can see that we could go from a very high linearity about 0.9973, and then between the panel on the left and the panel on the right, you can see without and with offset cancellation, you could make the readouts very linear, very flat. That's what you want. This is an example of bringing all of this together in an in-memory computing platform where you have an image frame-based pipeline where you have on the top you have a convolutional neural network, and then on the bottom you have an event camera with a spiking neural network. So the idea here is that a frame-based camera, which is a regular camera that we see, that gives you very high spatial resolution, right? But they give you very poor temporal resolution because you can only sample things at 30 frames per second or 60 frames per second. Whereas an event camera is essentially capturing changes in intensity. So it gives you an equivalent of 1,000,000 frames per second, but it does not give you the spatial resolution that you need. So if you look at biomimetic systems like the eyes of, let's say, eagles or other kinds of predatory birds, they have this amazing ability to kind of find a prey with a very high spatial resolution. So that was exactly the problem we were trying to solve, which is identifying a target and tracking. And we were trying to see how you can do that in a memory-centric way using these parallel pipelines of CNNs and SNNs. So on the top you can see that that there is a picture of a virtual environment of a CNN solving the problem in the CNN domain. On the right, on the panel, which is currently dark, that's an SNN, and the spiking neural network is working on the frame camera, and it's producing trajectories for operation. We took that concept further and essentially built a full system architecture around it with on-chip memory, RAM for in-memory computing, RAM-based processing elements, and an array of spatial processors to be able to solve this concurrent problem of SNNs and CNNs. And in a real world demonstration, you can see that when we embed that into an actual system in a drone, you can see that on the left there's the images from the image camera of the frame camera, and on the right you see the spiking neural network working on the event cameras. And what you get as a result of that, you get the best of both worlds. And by combining these kinds of pipeline units in a memory-centric architecture, you can get to this green spot, which gives you very high target acquisition ability, as well as the ability to track any kind of targets. So as I look at the future and the future of embodied platforms, we are going to see more of these kinds of juxtapositions of spiking networks, CNNs, different kinds of modalities of sensing. And the future of what is called physical AI today rests on the idea of having a memory agent with multimodal sensing, some sort of a planning agent which can be based on a language model like an LLM, or there has to be a reasoning agent which can be either a neural model or it can be a symbolic model, and then you can have some sort of a control and execution. And you can think about this being augmented with communication agents, where AI agents would be able to talk to other agents as well as humans. So this is where we have this prototype that we recently built using Neurosymbolic AI for embedded applications. The idea is to be able to perform not only from sensing to activation, that kind of a pipeline, which is often called a system one pipeline, but also augment that with a process of thinking and reflection, which is often called the system two pipeline.
I'm going to ask each of our speakers just to give us like where they see the future in this whole field.
I think the memory-centric architecture, which is flexible, where you're able to map your algorithms very effectively in such an architecture for energy efficiency, is what I feel is going to be the future.
Most of us, including myself, would have thought that the future of AI would look like flying cars, humanoids, robots, and all of that, right? So instead, one of the first things that AI learned to do was write poems, right? You don't know what the future is going to look like, and that's a part of what makes it exciting. That it also makes you pause and think about intelligence overall and creativity, and I think more profoundly what it means to be human.
We are going from the age of scaling to the age of thinking, which actually requires reasoning and a high context length for during inference. We are more focused on having a larger memory capacity and doing the compute near memory.
Well, I've actually been working in this area since 1995. I could not have predicted anything that it's been going on right now when I first started in this area. There are over 10,000 papers published every year now just on the topic of memristor. No one can actually pull all of that in and understand it. So there's going to be a lot of false starts, a lot of competition, which is going to be good. But how long this is going to take to finally come up to what I'll call a solution to the problem, I don't really know.